before. Is it good? Okay, great. So we want to highlight some of the posters that we have there in the back of the room. So for that, I will invite our first speaker, Hashan Fan, to give a very quick 2-minute flash presentation on the poster.
Good afternoon, everyone. I'm Hashan from Heron and East China Normal University. Very excited to introduce our work about the heatwave events, impacts on dissolved oxygen in Arabic estuary, which is influenced heavily by human activities like the deep channel and high nutrient loss. We use Schism and ECMO 3D coupled model to simulate the hydrodynamics and the biogeochemical situation in estuary during an extreme heatwave year of 2018. Our results show that the dissolved oxygen, or maybe not very clear, the dissolved oxygen decreased during the heatwave. Down. Thank you. Okay, thank you very much. During the heatwave events, the DO levels decreased a lot compared to non-heatwave periods. In the bathymetric jump region, instead of in a continuous decrease like that in the downstream. And the PA shows that heatwave events exacerbate the stratification in water column, and that resulting in lower DO levels or even hypoxia zones in the bottom water. That's all. Thank you very much. If you have any questions or suggestions, we could discuss later. Thank you again.
Now I'd like to call Renata Tascheit to present her poster. Thank you.
Okay. Good afternoon, everyone. My name is Renata. I am a postdoc here at CMCC in Lecce. And this work was actually done in partnership with the National Oceanography Center in Liverpool, which I did under the supervision of Anna Catavuta. And what we did was to develop a spectral nudging tool to be implemented in Nemo Ocean model. And for those who don't know, with spectral nudging, it means that we are able to pass the information from your parent model towards the child model, not only through the boundaries, but also you can put some constraints inside your inner domain. So what we want to do is to nudge the large scales of your inner domain towards the large scales of your parent, but you don't want to affect directly the small scale, so you want the small scales of your child model to be able to be free to evolve with your inner domain dynamics. So basically, what you can also define is where in your domain you want the spectral nudging to be stronger, and where you perhaps don't want to have any spectral nudging at all, like for example, near the surface or near coastal regions or even at shallow areas. So in this study, we did an experiment for the Adriatic Sea, where we implemented spectral nudging going towards the large scales of our parent driving model, which was the reanalysis product from the Copernicus Marine Service. And what we could see was that there was a significant improvement in the thermohaline properties inside our domain. Even though the spectral nudging we applied only for the tracers, we could also have an improvement on the inflow of saltier water through the Otranto Strait, which was a limitation in our previous model. And we could also see that despite we applied the spectral nudging only for the tracers, even the circulation evolved accordingly, and also at the very remote areas in the Northern Adriatic, for example, where we didn't apply any direct spectral nudging, even the kinetic energy in this region could evolve only with the inner domain dynamics of the model. So yeah, this was just a very brief introduction, and if you have any questions or if you are more interested, we can discuss later in the poster. Thank you.
Then I would like to invite our last poster presentation by Federica Benassi.
So hi everyone, I'm Federica. I'm a PhD student at University of Bologna and CMCC. You can see many familiar names that are present in this room that supervise my work. So this study is on the capability of the ocean to sequestrate anthropogenic atmospheric carbon. We know that this sequestration occurs mostly by biological processes, which means that phytoplankton that is working, let's say, in the uppermost surface layer of the ocean performs photosynthesis and, let's say, activates the trophic chain and basically processes this carbon dioxide that is dissolved in the uppermost surface layer, and ultimately this chain produces these carbon compounds that gravitationally sink to depth. What you have to keep in mind is that the greater this depth of sinking is, the longer this carbon is sequestrated from the ocean. So as you can see, this process that is called the biological carbon pump is driven by depth. Greater depth means longer sequestration, but also it depends on productivity, because the more productivity we have, the more carbon compounds we produce. And the majority of productivity is concentrated in the coastal regions that are shallower. While, of course, the open ocean has the capability to increase this length of sequestration of these carbon compounds. So what if there's some sort of mechanism that laterally transports these highly productive shelf waters towards the open ocean? And this is exactly what we want to estimate. How much of this carbon is laterally transported through currents and through, let's say, yes, these processes. And the global estimation of this transport is missing. So the majority of these processes are mesoscale and sub-mesoscale, which means that they are also quite hard to monitor because they're related to high variability, which is on shorter time scales and space scales. We use the satellite data, so purely observations that have a high spatial resolution and a very long time series of daily data. And we developed this unsupervised learning framework to systematically detect these sub-mesoscale and mesoscale structures that is based on k-means clustering. So here I am showing you an example on the California current system. And you can see that this green cluster basically finds, the clustering algorithm is fitted on chlorophyll and sea surface temperature anomalies. And you can see that it identifies this green cluster that contains the majority of high chlorophyll anomalies, which may suggest that there's some sort of intrusion of highly productive waters in open ocean. And you can see this cluster actually identifies these filamentary structures that are filaments, upwelling filaments that laterally transport the structure. By using this framework, we can give an estimation of the content, of the carbon content of these structures. And we did this for the eastern boundary upwelling regions that are the most productive regions, the most productive ocean regions. And the algorithm systematically finds these hotspots of filamentary activities. We gave an estimation that is about 23 teragrams per year. And also we try to look at how primary production on the shelf and mesoscale activity interact in modulating the seasonality of this. But for other, if you want to discuss more, I'm here. Reach me out. Yep.
Please note that the posters are on display there at the back of the room, so please stop by and talk to our presenters if you have any questions. And see you back at 4. Yeah, if you could take a seat, we will get started again now with the flash poster presentations. So I would like to invite Gabriel Gallegos Diaz Barroso to start. If you can stand here and tell us why we should come to your poster and what is the main takeaway in 2 minutes.
Yes. Do I have the no? Okay. Hello. Thanks for coming. I'm trying to describe very fast the system, which I have to. We move a little bit down? Perfect. Yes. Okay. Grazie. Ah. So the aim of this work is like trying to describe how the climate oscillation is modeling in the ocean currents. So we have here the Gulf of Mexico's main circulation, which is part of the much greater interchange of heat in the ocean. So we have a lot of water from the Caribbean Sea coming through. It's hot water, and then exports this water to the North Atlantic. So this variability of exporting heat to the North Atlantic, we will have a feedback into the NAO, and also there's a feedback in with the ENSO and with the ENSO oscillation. So I decomposed the Gulf current circulation in 4 principal modes through the EOF components. And then each principal component, which is described in time in of the circulation, of the variability of circulation, I did a cross-spectrum analysis with the NAO and with the ENSO. So there are shared correlations, significant ones, within several frequencies. But the main issue that I want to share with you is like how does the heat interchange are modulating the entire world circulation, because the heat variability will affect eventually the NAO and the ENSO through the winds of moving hot water to one place to another. And this can be like a system of heat interchanges. So we have a layer of heat interchange of the atmosphere, which is distributing heat along the world in the atmosphere, and then we have another layer in the ocean. And we have also well-described climate oscillations as like an NAO and QBO and the ENSO, and we have can describe this system like a complex oscillation system. If you want to, we discuss further, but it's like having the descriptions of the variability of circulation of the atmosphere and the ocean through the climate oscillation variability. So that's the main issue I want to share with you. Thank you.
Thanks a lot. I now invite Marco Boetti to give his speech.
Thank you. Hello, everyone. Hello, everyone. I'm here to present the work that my colleagues and I have done at CMCC on the modeling of and the study of storm surge forecast in Venice. So as some of you may know, in Venice there has been, in the last few years, has been built a system of barriers called MOSE. These are a system composed of several modules that are located at the 3 main inlets of the lagoon, and they are activated whenever the surge rises in order to mitigate the damages to the city. So this, however, represents the main gap with modeling, because there have been so far very little work in trying to represent them. And what we have done is to develop an immersed boundary method that we embedded in our urban scale model SHIFEM to represent and to mimic the effect of these barriers. And so we tested our approach in the November 2022 storm event. It was one of the strongest surges ever recorded in the lagoon, and during which the MOSE was activated 4 times. In our working flow, we use the Mediterranean forecasting system provided by Copernicus for the regional data that are used to force the urban scale model. And what we found is that our approach works very good. You can see here the time series of the sea level in which we reported the SHIFM outputs and also the tide gauge measurements. So we have basically two networks, one outside the lagoon and another one inside it. So you can see that the use of these immersed boundaries is very effective in reproducing the actual sea level at these measurement points. And as a last point that I want to show you is these maps, because our work now allows us to produce these maps that provide, in this case, also sea level height. And we have produced 2 runs, one with the immersed boundary here on the left, and another one without it. So we can compare the real state of the lagoon with what-if scenarios. And what we found is that at the peak surge, the difference of these 2 different dynamics can lead up to 1 meter in water level inside the lagoon. So if anybody wants to have more explanations, I will be glad to give them later on. Thank you.
Thank you very much. And we now have the last poster presentation, also on Venice, from Martin Galcani.
Hello, everyone. Thank you so much. I'm a PhD student at the University of Padua, and this work is based on the Restart AquaSmart project fund. We started like 3 years ago with the group at the University of Padua, which we call it Signet. And this is the project which we started to develop a real-time and also cost-effective device. So, as you know, the Venice Lagoon environment is a bit challenging because of the industrial activities that can affect on marine's life, and also raising the sea level can be affected for the human activities, and also living the people that they're living in coastal areas. So we should monitor it continuously, and one of the challenges is sampling. Sampling is a bit difficult if you want to do manual sampling. So, and also some parts of the Venice Lagoon is not very easy reachable. So we, with collaboration with the biology department at the University of Padua, we developed this device that you can see here. But this is just the first phase. We just wanted to be sure that it worked and everything works well. So we put at the beginning 7 sensors on that. So the pH sensor, conductivity, turbidity, temperature, dissolved oxygen, and also a liquid level and GPS. To know that the liquid level was used to be sure that the device is inside the water, and also GPS to know the exact position of the device. So after we deployed it inside into the Piovagos River, which is close to our department, in front of our department, and we left it for a couple of weeks. We reached to good results, and then we went to the next phase, which we deployed it into Venice Lagoon. But Venice Lagoon is a kind of tricky environment, because in the winter and in summer, the situation completely be different. And in summer, biofouling activities is too high. So as you can see, the device completely ruined after a couple of weeks. So we changed it to a plastic prototype. And now we deployed it in Piovego's River and also one in Chioggia. So now we are waiting for more results. And here is the panel that you can see the results by having the access to Grafana's panel. And it's really easy to have the device for the other environmental conditions, like in the rivers or in the other parts of the oceans, or even because also we use LoRa technology. So even like 10 kilometers from the coastal areas, you can still have the data transmission. If you have any other questions, my poster is over there, so I'm available for any questions. Thank you.
Thank you so much. Yes, there are still also more posters, so make sure to stop by. And I would now like to, well, thank you for the attention so far, and I give the word to Abe for the breakout introduction.
Okay, here comes the most difficult